Good morning. Microphone is working? Okay, let me start by asking if there are any questions about yesterday's lectures that you thought about over dinner or couldn't sleep at night because you were worrying, asking about the questions. Okay, so everyone slept well. So what I'm going to do is, again, we're going to calculate the gravitational production of a spectator field that is quantum in the evolving background of a Friedman-Robertson-Walker model, and we're going to take the evolving background as classical. So this is known as a semi-classical calculation. So part of it will be classical, the evolution of the background field, and part of it will be quantum, the quantum aspects of the spectator field. So yesterday I almost finished the background that we will need in Friedman for FLRW model. And eventually we're going to take the background as being driven by a scalar field known as the inflaton field. But we will also approximate the evolution of the background by looking at a de Sitter space solution and a matter-dominated solution and a radiation-dominated universe solution. So what we ended with yesterday is for a constant equation of state. The equation of state relates the pressure to the energy density. W is equal to P over rho, the pressure divided by the energy density, that A prime over A to the fourth, which is the square of the expansion rate, and this is proportional to some, say, HE squared times A over AE to the minus 3 times 1 plus W. So here, HE and AE in general is general, but we will take it eventually to be the scale factor at the end of inflation. I'll define the end of inflation today. And HE will be the expansion rate at the end of inflation. So we have a differential equation for A, and there are simple solutions to this. And in de Sitter space, W is equal to -1. This would be a universe that's dominated by a cosmological constant. Then we can write A over AE is 1 over 1 minus AE HE times eta. And here eta will go from minus infinity to 0. So if eta is equal to 0, A is equal to AE. In a matter-dominated expansion, W is equal to 0, and A over AE is 1 plus 1/2 AE HE eta squared. And this is just simply found from solving this differential equation. And the final thing I'll take would be for a radiation-dominated model, W is equal to 1/3. W is equal to 1/3. And A over AE is 1 plus AE HE eta. So in a radiation-dominated universe, the scale factor grows as conformal time, for large conformal time. In a matter-dominated universe, it grows as eta squared. And we can, eta is only defined by d eta is equal to dA over A. So we can add or subtract to eta anything that we want. And in general, we can take eta E equal to 0, which is implicitly what I've done here. So let me make a table that we're going to use. Sorry?
Can you explain the inequality for eta? Why the eta is greater than the root of smaller than infinity?
Yes. So we're going to take de Sitter as a sort of an initial condition. And if eta is equal to minus infinity, A will be 0. So we're going to start the universe at A equal to 0 in a de Sitter phase, then transition at the end of inflation at eta equal to 0 to a matter-dominated phase. Thank you for the question. Sorry? I'm sorry, yeah. Small difference. Thank you. So I'm going to look at various epochs, at how A of eta changes, H of eta, and the Ricci scalar R of eta. So I'm going to imagine inflation with eta less than 0, greater than minus infinity. And A over AE is as written there. This, again, is over there, 1 over 1 minus AE HE eta. And in the matter-dominated phase, which would be eta greater than 0 and smaller than some value of eta, we'll call it now the reheat value of eta. And for a radiation-dominated phase, it's 1 plus AE HE eta. Okay, good. And here, during the de Sitter phase, or during inflation, the expansion rate is roughly equal to a constant. During matter-dominated phase, it goes as 1 over A cubed. And during the radiation-dominated phase, it goes as this square, 1 over that squared. So I'll just write proportional to 1 up to eta, 1 over eta squared. Now, for the Ricci scalar, the Ricci scalar this would be minus 12 HE squared and minus 3 HE squared I'm sorry, to the 6th. And in a radiation-dominated universe, the Ricci scalar vanishes. So eventually we will track the dynamics of A, H, and R described by the evolution of the inflaton field, but this will be some approximations that we will return to and use.
Expressions for the scale vector for radiation domain universe.
I'm sorry, say again?
The expressions for the scale vector for the radiation domain universe.
Here?
Yeah.
Well, let me just write this as being proportional to eta. Okay? And we can connect this. There'll be some eta reheat that we can do some connection, and I will eventually do that. Okay, now all models of the early universe today involve inflation. So I want to define what inflation is, the criterion for inflation, and how scales change during inflation. So this is something I'll describe as inflation. And its aftermath. So inflation and what happens after inflation. Okay, so I want to look at two length scales in the evolution of the universe. One is a physical length scale. So the distance between two co-moving points. So if the points are co-moving, if two things are co-moving, they are at fixed coordinate x, and their distance increases as a increases. So I can define a physical length dp, p for physical, as some fiducial length times a over a0. So as the universe expands, as a increases, the physical length increases. And we can write, and let's imagine that 0 is for today. So 0 stands for Tuesday. Okay? And I will also define a Hubble radius, a Hubble distance, which is h to the minus 1. And h changes, h decreases generally in the matter-dominated or radiation-dominated universe. So as h decreases, the Hubble radius increases. And this is proportional to 1 over the square root of rho. From the Friedmann equation, h squared is proportional to rho. And h to the minus 1 is proportional to a squared for radiation. And it's proportional to a to the 3/2 for matter. And it remains constant for a lambda-dominated universe. So let's see how these things change with how distances change, either the physical distance or the Hubble radius with A. Well, the physical radius just is proportional to A. So this is, let's say this is 0. This would be the value at Tuesday. The Hubble radius is going to grow with A, and it grows with a different power law, whether it's matter dominated or radiation dominated. So let's imagine, this is supposed to be linear. Let's imagine today there is some value of the Hubble radius. It's going to decrease as we go back in time during the matter-dominated phase as a to the 3/2. And then during the radiation-dominated phase, it's going to decrease faster as a squared. Not a very pretty picture, but I think you might get. All right, so here, let's look at some value of A, which corresponds to the time at which the microwave background radiation last scattered. So as we look out in space back in time, we see the last scattering surface of the microwave background radiation, and that would correspond to some value of A that I'm calling ACMB. And it actually happens in the matter-dominated phase. So let me put it there. Now, there are physical scales today that we observe that's smaller than the Hubble radius, that was larger than the Hubble radius when the microwave background radiation last scattered. So when we look at the microwave background radiation, we can see scales on the sky that have correlations in them that were larger than the Hubble radius when they were produced, when we observe it at ACMB. And this is hard to understand because the distance over which a light signal can be propagated is the Hubble radius. And here we're seeing correlations in the CMB that's larger than the light travel distance when it was produced. How can we physically understand that? Well, we can physically understand that if at some early time, H does not increase as A, but say is roughly constant. So if A is roughly constant, then there will be a time at when the physical distance will be smaller than the Hubble radius. So this is the Hubble radius. And here the physical distance, dp, is less than the Hubble radius. So you can imagine putting correlations or doing something causally to produce the correlations that are observed later when we look at the microwave background radiation. So what we want to have is a period where the Hubble radius, which is this, is going to, as you look back in time, decrease more slowly than the physical radius. So if we look at the Hubble radius, this is proportional to A over A dot. And divided by a physical radius, which is proportional to 1 over A. I'm sorry, proportional to A. So if we take the ratio of dH over dP, it's just going to be 1 over A dot. And I would prefer actually to do this the other way around. I'm very sorry. So this ratio of dP over dH is A dot. And in order to have the correlations, to have the physical scale, dP, smaller than dH, we're going to want to have A double dot at some point greater than 0. So A double dot, a period of expansion where A double dot is larger than 0 is what we define to be inflation. All right, A double dot over A from the Friedman equations is minus kappa over 6 times rho plus 3p. So now if we want A double dot to be positive, we have to have an equation of state such that the energy density plus 3 times the pressure is smaller than 0. Now, a negative energy density would violate various conditions, strong energy conditions in GR. So we have to do something with the pressure. And a model for this is de Sitter. So if we have a universe that's dominated by lambda, the equation of state is P is equal to minus rho. So rho plus 3P will be negative since P is equal to minus rho. So inflation will be an early universe epoch with accelerated expansion when rho plus 3p is negative. So somehow we want to envision the evolution of the universe that starts in inflation or has inflation at some early time where A double dot is larger than 0, rho plus 3p is negative, then somehow this contribution to the energy density goes away and then smoothly goes into either a matter-dominated or radiation-dominated phase. How do we do that? Well, in particle physics, a tool is a scalar field. And it's often said, and sometimes it's the only tool. And there's a saying that if your only tool is a hammer, everything you see appears to be a nail. So we're going to have a hammer of scalar field theory, and we want to work on this problem. How do we have a quasi-de Sitter phase or accelerated expansion that's there naturally and then goes away? Then we're going to use the tool, the hammer of scalar field theory. So the nice thing about this sounds like a little dodgy idea, is inflation is driven by the dynamics of a scalar field. And if this sounds a little dodgy, a little dicey, then you give it a really nice name. If you can give something a nice name, it sounds more believable. And this scalar field goes by the name of the inflaton. Okay, so it's a good name. We don't know the origin of the scalar field, but we have a cute name for it. That's pretty good.
Is there reason to the inflaton should be scalar field?
No. We think that if the expansion is homogeneous and isotropic, driven by some field, then it doesn't have a preferred direction. So you have to work very hard to have it be a vector field or a tensor field. And the scalar field is the natural, easiest thing to imagine. Okay, so we don't know. No is a word that's very dangerous to use in physics, especially in cosmology. We don't know anything, what drives the dynamics, but we can model it in terms of a scalar field. Perhaps it is a fermion condensate or something that behaves as a scalar field, but let's just take it to be a scalar field and follow this. All right, so let's study the dynamics of the scalar field, the dynamics of the inflaton in FRW. So assume there's a scalar field. And let's just call it this phi. And in Minkowski space, the action would be and in general, we could write a potential, but now let's just assume that the potential is just harmonic, 1/2 mu squared phi squared. So that's the action for the scalar field in Minkowski space. And now we want to promote this to FRW, and we're going to do this in the way that we described yesterday. Eta mu nu will go to G mu nu, where G mu nu is the metric for FRW, and the square root of minus G is going to go to A cubed in FRW. Here I'm in time. In coordinate time, not in conformal time. So the action in Minkowski, I'm going to assume consistent with the assumed symmetries of FRW, homogeneous and isotropic, that phi is spatially homogeneous and isotropic. So the action simplifies in Minkowski. The square root of minus g is a cubed, so this would be a cubed. Okay, good. And from this, I can calculate the equation of motion using the Euler-Lagrange equation. And the equation of motion for the scalar field, the inflaton field, is phi double dot plus 3h phi dot plus mu squared phi is equal to 0. So this would be familiar in Minkowski space where h would be 0. And in general, we can replace mu squared phi squared by some potential of phi. So we have the action. From the action, we can calculate the stress energy tensor and calculate the energy density and the pressure. Recall from yesterday, the stress energy tensor let's make this mu alpha, g nu beta. The usual expression for the stress energy tensor. And T00 is equal to rho. And TII is equal to minus P GII. So we can calculate rho from the stress energy tensor because we have the Lagrangian. And we can count also the pressure. And if you do this, you find that rho plus 3p, which is of interest if we want to have inflation, is 2 phi dot squared minus mu squared phi squared. Okay, so if we have the potential term for the inflaton field in magnitude larger than the kinetic term, then we will have rho plus 3p to be negative. And then if phi dot squared becomes smaller than mu squared phi squared, rho plus 3p will be positive and will go into a normal matter or radiation dominated universe. So here we have a nice harmonic potential. And if the scalar field, for some reason, is displaced from its minimum, it will and displaced from the minimum such that the potential term in magnitude is larger than the kinetic term, then we will have inflation. And then as the scalar field evolves to the minimum following the equation of motion, eventually phi dot will become larger and larger and larger, and phi dot will become larger, 2 phi dot squared will become larger than mu squared phi squared, and inflation will end. So there'll be some value of phi corresponding to the end of inflation. So here the scalar field is inflating, driving inflation. Just following the simple equations of motion, phi dot is increasing, and eventually it will go into inflation will end. Let's see, so I think I have a picture of that. Now here I have assumed that the inflaton potential is just mu squared phi squared. There are many, many, many models of inflation which have different, more complicated inflaton potentials. And there are models of inflation which have more than one scalar field driving the dynamics of inflation. So there's a standard inflationary picture, but there's not a standard inflationary model. But there is a simple inflationary model that I will use often, and that's just a single field with a quadratic inflaton potential. So as described here, the potential, the scalar field starts at some large value of phi, evolves under the influence of the potential according to the equation of motion, which is behind there, and then eventually inflation ends when A double dot becomes negative, when the kinetic energy starts to dominate. Now, the inflationary potential is probed by CMB observations. The CMB observations rule out this simple inflationary potential. But the CMB observations are sensitive to the value and the value of the potential and the first and second derivatives of the potential at some large value of phi. So the simple model is ruled out by CMB measurements, but CMB measurements probe the inflation potential some 60 or so e-folds before the end of inflation. We, in this lecture, will often be interested in the inflaton potential near its minimum, and you can imagine the inflaton potential near its minimum being well described by harmonic potential, whereas it's not a harmonic potential at some larger value. So this is a result of a numerical integration of the inflaton field equations, phi double dot plus 3h phi dot plus v prime of phi is equal to 0 for the harmonic potential, a quadratic potential. And this shows the evolution of the scale factor near the end of inflation, the scale factor, the Hubble expansion rate, the absolute value of the Ricci scalar, and the value of the field divided by the Planck mass. And this is near the end of inflation. as a function of conformal time over AEHE. So 0 here defines the end of inflation, and A will be equal to AE, and H is equal to HE. So that would be 1 at the end of inflation. So the scalar field starts here and then slowly evolves, and then as it gets nearer and nearer the bottom of the potential, it will become larger and larger, and then it oscillates about the minimum of the potential with decreasing amplitude. So the dashed lines here correspond to a negative value either of the field itself or the Ricci scalar. So the Ricci scalar starts with something about 10 deep in inflation. Then the Ricci scalar decreases and then oscillates about 0. So let me stop here and absorb this for a little bit and see if there are any questions. This is just a numerical integration of the inflaton field equations. This is showing the results in a different way, sort of a larger range of eta. And it's comparing the results for the quadratic model of inflation to this simple model of inflation where you start exactly in de Sitter and then transition to a matter-dominated phase. Ah, there's a pointer. So if it would be pure de Sitter space, then H is constant during a de Sitter phase, and then we say, de Sitter phase ends, and H starts to decrease as a matter-dominated phase. That is
Yeah, could you check the microphone?
How about now? Was it on before? Something in my pocket turned it off. I don't understand. Thank you. Okay, and also, this is a graph of H divided by HE after the end of inflation, and this just decreases as a to the -3 halves for this analytic approximation. But what happens numerically is H oscillates at the end of inflation. There's an oscillatory form at the end of inflation, and this oscillatory behavior, this oscillatory feature, is due to the scalar field oscillating about the minimum of the potential. Yes?
Some plateauing makes that we have some confusion to the e-folding after the inflation?
Well, when we calculate the e-folds, before the end of inflation, we end at eta equal to 0. So eta equal to 0 is the end of inflation, where numerically a double dot will be negative. Over here on the left side, this plateau in A. In H? Yeah, so this only is after the end of inflation. H is constant. The analytic approximation is H would be constant during inflation, but in fact, H is not quite constant during inflation because there's a little bit of evolution because phi dot is changing. There's a contribution to phi dot, even though it's small. Yeah, the usual calculation of E-foldings will do A here as a function of eta. So to do the calculation of the number of E-folds, you really want to look at the actual behavior, numerical results, rather than the analytic approximation. So I think that's sort of the question you're asking. If not, let's talk about it after. Okay, thank you. So I talked about R. These are comparison of the quadratic inflaton model and this analytic model. In the analytic model, R is -2 during the de Sitter phase, but actually it becomes larger and negative as we go back before the end of inflation. And after the end of inflation, in the matter-dominated phase, the analytic model will start at -1/2, so it will go from -2 to -1/2. There's a discontinuity in R, and again, it will oscillate around 0 in the numerical model because the scalar field is oscillating around about its minimum. So I said the scalar field is oscillating about its minimum. Here is a graph of W, the equation of state for this scalar field as a function of the scale factor. So the equation of state approaches -1 during inflation, so it looks de Sitter-like. Then it starts to grow, and after the end of inflation, it oscillates. So the scalar field is oscillating about the potential. As it reaches the maximum, as it oscillates, it looks like W is equal to -1. And then at the minimum of the potential, where there's 0 potential energy, it looks like it goes from -1 to 1. So it goes between something that looks like kination to something that looks like lambda, and the average value is 0. Okay, so that's the quadratic model of inflation, but there are other models of inflation. One popular model of inflation is known as a hilltop potential, and this would be a potential for an example of a hilltop potential. So rather than just be harmonic, this is a hilltop potential where the potential for small values of phi becomes very flat, and then it evolves, and here's where inflation ends, where the number of E-folds before the end of inflation is 0, and then it oscillates about the minimum of its potential. Now, the hilltop potential is motivated by string considerations, supergravity considerations. So you say the magic word string theory, and people nod their heads, say, yes, it's a good model. Yeah, I like that model. But, you know, I always think that often when people say it's motivated by string theory, you could substitute the word asparagus for string theory with the same meaning. So, you know, be that as it may, it's a popular model of inflation. So here, your 40 EFODs from the end of inflation, 40 EFODs in the scale factor, 10, 5, and as you go closer and closer to phi equal to 0, you go to very, very large number of EFODs before the end of inflation. So CMB observations will be sensitive to the potential around here, maybe 40 EFODs or so before the end of inflation. And we will often be interested in the behavior here where it is approximately quadratic. This is a graph similar to the one that I showed for quadratic inflation. So the blue curve is the scale factor divided by A sub E. So at the end of inflation, eta is equal to 0 and AE is equal to 1. And the expansion rate divided by the expansion rate at the end of inflation. Numerically, for the hilltop potential, H is very constant at early times. Again, the Ricci scalar over 6HE squared is roughly constant. Then at the end of inflation, it starts to oscillate as before. The scalar field over the Planck mass is roughly constant. Then it grows and then oscillates about the minimum of the potential. So this is examples of two inflaton potentials. So these simple models of inflation, this picture of an inflaton field evolving under some potential, can describe the evolution of a universe that begins in approximately de Sitter space, quasi de Sitter space, where A double dot is positive, which is the definition of inflation. And then as it approaches the minimum of the potential, the kinetic term starts to dominate. And as it oscillates about the minimum of the potential, the average value of the equation of state is 0. So it goes into a matter-dominated phase. Of course, that cannot be the end of the story, because we know that for much of the early history of the universe, it was radiation dominated. So we have to consider the possibility of how we reheat the universe. When you study cosmology for the CMB, you talk about recombination, when the electrons and protons recombine to form neutral hydrogen. And of course, this is a misnomer using the word for recombination because they were never combined to begin with. And this is also a misnomer of talking about reheating because it's possible the universe had no temperature. It wasn't heated to begin with. So there's going to be an approximation here. So at some time when the scale factor of the universe was A reheat, the inflaton field conveniently decays and gets out of the way, and it decays to relativistic products, and the universe reheats. Okay, this would be a good time to stop for the break because now I'm finished describing the background field evolution. So we're going to start with a universe that's approximately in de Sitter space. Then the universe evolves to become matter-dominated, then radiation-dominated. Now I want to introduce a spectator field, and I'll start with the scalar field and see how the spectator quantum field behaves with this background evolution of the gravitational field.
Okay, thank you. Any questions? If not, let's thank Rocky.
And for the spectator field, I will start off assuming that it is a scalar field phi. And after I study the gravitational production of the scalar field, I'll go on to fermion fields, to massive vector fields, to spin 3/2 Rarita-Schwinger fields, and to tensor fields. So let's start with the scalar field phi. And the action, I'll always be starting with the action, d4x to square root of minus g. Now, I'm not quite finished writing this, but you notice that this is just a normal derivative because for the covariant derivative of a scalar is a normal derivative. Now, I'm going to, just to make things interesting, add another term here. Where R is the Ricci scalar and C is some dimensionless constant. So C, phi squared R, is a dimension 4 operator. And I'm going to assume that C is a constant. So this will be, if C is not equal to 0, a non-minimal coupling of the scalar field to gravity. So the simplest minimal thing you could do is to have C equal to 0. Now, why do I add this? Perversion, I don't know, just to make things complicated for students? No, that's not the only reason. So one reason is from the point of view of effective field theory, there's no reason not to include it. It's a dimension 4 operator. Why not write it? And it is the only dimension 4 operator containing R mu nu, R alpha, mu, beta, gamma, whatever, either the Riemann tensor, Ricci tensor, Ricci scalar. This is the only dimension 4 operator that contains that. And another reason to add it is C equal to 1/6 will be a special value and it will be known as a conformal coupling. And we'll see why it is the conformal coupling in a moment. So C equal to 1/6 is a special value. Another special value is C equal to 0, and that's known as minimal coupling. So when I study C equal to 1/6 for a scalar field, it will give us insight to other theories, like for fermions, that are conformally coupled, except for the mass term. All right, so if we start with that action, we can find the equation of motion. That's the covariant action. And here, box it's the general relativistic, the covariant box, and it is G mu nu, d mu d nu, phi, minus, and it's going to bring in the Christoffel symbol. So this is how gravity, how the scalar field will know about gravity. In FRW, box phi is phi double dot minus a to the minus 2 Okay, this is something that's just easy to work out, straightforward at least. And I can calculate the stress energy tensor and take the trace. Okay, and now we see the trace of the stress tensor will vanish, and the scalar field phi will be conformally invariant. Sorry? M squared phi squared, you are correct. Thank you. So if C is equal to 1/6 and the mass is equal to 0, the trace of the stress tensor vanishes. And it will be conformally invariant. So in order to have gravitational particle production, we either have to have m not equal to 0 or c not equal to 1/6. Now let's do conformal time.
아쉬운데
Is there a question? No. Yeah.
So why are you just M scale by scale instead of zero potential fluid pi?
So you want to make things more complicated, that's okay. I'm doing the simplest possibility, and maybe for homework, you can have a more complicated model. So this is a free scalar field. So what I'm going to do is to calculate gravitational particle production of a free scalar field. Okay? Since I'm a cosmologist, I love conformal time. So and this is in FRW, conformal time in FRW. So the G mu nu there is going to bring in factors of 1 over a squared. Remember, the square root of minus g is a to the 4th. And G mu nu in FRW. So the square root of minus g brings in an a to the 4th. G mu nu brings in an a to the minus 2. So the kinetic terms have a squared, and the potential term and the non-minimal coupling term will have factors of a to the 4th. Now we're going to do gravitational production. We're going to do a quantum field. And this is not a good place to start because the kinetic term is not a canonical kinetic term. So in order to find a canonically normalized field, we're going to define a new scalar field, phi. This is without the little top and bottom, as A times phi. So if I do that in terms of this new rescaled scalar field, the action will be d eta d3x, and it has a term that almost looks, well, looks good from in this point, would be d eta phi squared minus 1/2 So we have a canonical looking term for the kinetic term here at the expense of this additional term and a sort of funny looking effective mass term there. I don't think so. But then for the particle production, you would have to consider processes that involve phi. So it makes a more complicated, but still an interesting theory to study. So I have a request to make the lectures more complicated. Is that so you can blame him at the break? Okay, so we want to quantize the field phi, and we're going to do this with a Hamiltonian approach. So, you know, for quantum field theory, when you quantize something, you want to do it in the Hamiltonian approach. And so we're going to construct a Hamiltonian. And of course, pi, and let's see what I want to do. The canonical variable okay, we can get that simply from the action. Good. And so we can form the Hamiltonian. So this is the Hamiltonian. And can anybody guess why I wrote pi times phi in terms of 1/2 phi pi plus pi phi? Sorry? Right. Good. We'll consider them to be operators, and it will have some commutation relationship. So I'm looking forward to making it operator. All right, so I can look at the operator equations of motion. This someplace. And pi prime and the equation of motion. And I would define some effective mass squared. And let me just leave it as the effective mass squared there. But okay, let me just write what it will end up being is k squared plus m squared. Let me just stop there. So there's an effective mass squared that involves m, h, h prime, which will involve r. So that is the effective mass squared. Recall the Ricci scalar has mass dimension -2. So this looks like a normal equation of motion, except for this factor of A, and in the effective mass squared, there's this factor. So if A is equal to a constant, say A equal to 1, and R equal to 0, in other words, if we're in Minkowski space, then the effective mass squared is just the mass squared, and it's the normal thing that you would expect for a scalar field. But here you see in the equation of motion, the effective mass is going to change as the universe evolves. The effective mass, the term of the effective mass squared here, will depend upon A, 1 minus 6C, and R. So we're going to do quantum field theory where the effective mass is going to change with time. And that it will be the basis of why there would be particle creation. Now, we're going to assume that solutions here, it's a second order equation, that the solutions take the form familiar from quantum field theory. We're going to introduce ladder operators AK and mode functions U of K. And we will write the mode functions UK Okay, so this is familiar for Minkowski space quantum field theory. So we've introduced ladder operators. AK and AK dagger. And UK, the mode functions. Form an orthonormal basis labeled by a co-moving wave vector K with wave number Now, often I'll write the co-moving wave vector as K. It's not a 4 vector, it's the magnitude of a 3 vector. Good. Now, the first appearance of the quantum in these lectures will be the fact that the ladder operators obey the commutation relation AK dagger 2 pi cubed. I'm not going to worry about an H bar. And all others will vanish. Okay, so this is sort of straightforward quantum field theory. We're just following our nose. The only thing that will be different is that the mass is going to be time dependent. So the mass term in the equation of motion will be time dependent. So the wave equation is second order. Wave equation is second order. And so for each wave number, it admits a 2-dimensional space of solutions. And sort of for the rest of these lectures, it's going to consist in identifying a good basis of the mode functions to span the space. So for instance, we're going to want to span the space such that UK corresponds to positive frequency modes. Positive frequency modes. And UK star corresponds to negative frequency modes. So UK and UK star form an orthonormal basis. So there is a Wronskian condition that has to be satisfied. And the Wronskian condition is D3X, UK, UQ star prime minus UK prime, UQ star and the Wronskian condition will imply something that we will use before, use again, chi k star prime, prime is d by d eta, minus chi k star chi k prime is equal to I. So these condition, that condition guarantees that UK and UK star are the complete orthonormal basis. So the wave equation becomes IK double prime of eta plus some frequency squared of eta times chi k of eta is equal to 0, and omega k squared of eta is k squared plus a squared of eta m squared So of course, we just recover normal Minkowski quantum field theory. If A is equal to a constant, we can set it equal to 1, and R is equal to 0 if we go to Minkowski space. Recall that in de Sitter space, R is equal to minus 2h squared. So this term can be negative. So omega squared need not be positive. So let me just show you. So if C is equal to 1/6, the term in omega k squared that is proportional to R will vanish. So if C is equal to 1/6, conformal coupling, we will always have omega k squared positive. But if C is equal to 0, the minimal coupling, then during the inflationary phase, and in fact, even after the inflationary phase, R can be negative and omega k squared can be negative. So this is a figure from looking at quadratic inflation showing that conformal and minimal couplings are very different. Here I've picked a value of K, a value of M over HE. So this is the figure for conformal coupling. Looking at omega k squared, it's always positive. It's roughly constant deep in the inflationary era, and then it starts to grow as A squared eventually. This is for the minimal coupling case, for C equal to 0, omega k squared starts to be positive. Let me see if I can write this on the board here. Okay. So if omega k squared, if for conformal coupling, as A goes to 0, so conformal coupling would have C equal to 0, so there's the term A squared R, but as A squared goes to 0 for both conformal and minimal coupling, omega k squared is K squared. Then as A grows, eventually these terms will dominate. If C is equal to 1/6, eventually it will just grow as A squared. But if C is equal to 0 and R is negative, omega k squared can be negative. So this is much different than what we would encounter in Minkowski space, where we expect omega k squared to always be positive. All right. So in Minkowski space, the positive frequency solution And the normalization factor comes from the Wronskian condition there. So it's normalized to satisfy the Wronskian condition. So when this set of mode functions are used to construct the field operator, so I have to apologize a little bit about notation. This is not the scale factor. It's the ladder operator. To really be, I really should put little symbols over this to signify it is a ladder operator. So this associated ladder operators define a vacuum state such that it is annihilated by all the AK. So Minkowski spacetime is privileged insofar as all inertial observers agree on the absence of particles in this vacuum state. All inertial observers. But if we have Minkowski space around us, if we have a non-inertial observer, they're not going to agree that the vacuum state is absence of particles. This is known as the Unruh effect. So that's Minkowski space. Now let me talk about asymptotically flat spacetimes. So now I'm not going to consider Minkowski space. I'm going to start with a space-time that's asymptotically Minkowski in the far past and in the far future. So I'm going to assume that A of eta this is A of eta to at minus infinity. Is some AN this goes to A out. And these are real and positive. So the solution to the mode equations, I'll have chi k n I also have to normalize it to agree with the Wronskian conditions. And chi k out, this is the asymptotic value. So I have different mode functions for in and out. So I can write phi k, I'm sorry, I can write phi of eta and x either in terms of the in or out mode functions. Ah, so I can write it in terms of the in mode functions, or I can equally well express it in terms of the out mode functions. So these are equivalent, and the freedom to move between them is captured by something that's known as a Bogolubov transformation. So I want to consider matrices alpha k, beta k star, and alpha k star that are elements of SU11. In other words, alpha k squared minus beta of k squared is equal to 1. So in matrix form, I can write AK chi k plus AK dagger chi k star. And now I can insert the SU11 matrices. And this I can write as AK dagger times alpha k star minus beta k star alpha k. I'm just going to insert unity. Okay, so the product of these matrices, if they are elements of SU11, this is just the identity matrix. So I can write this as transpose this term times some other combination, I'll call it a tilde, so chi k tilde would be alpha k times chi k plus beta of k times chi k star. And I can define this as some other ladder operators. So I can use a Bogolubov transformation to go between the mode functions chi of k to some other mode function chi k tilde, and an associated ladder operator that moves between ak and ak dagger to ak tilde and ak tilde dagger. And the tilde operators obey the commutation relation, and the mode functions in the tilde basis also obey the Wronskian conditions. So the field operators phi admit a one-parameter family of solutions related by SU11 transformations. Great. We're almost done. Now I'm going to just say the tilde operators we can write as out, and the untildes as untildes as in, and chi k out, mode functions chi k out, so I can relate chi k out to chi k in plus chi k star in, and the ladder operators in the out basis oh, there's a minus. We can invert these and use the Wronskian conditions to write alpha k
Professor?
in terms of the mode functions. And similarly, beta of k.
Professor? I have a
Yes.
question. I'm wondering why you assume that space-time is asymptotic flat when moving time goes infinity.
Why I assume space-time is what?
Why space-time is asymptotic flat when moving time goes infinity.
So what I will end up assuming is not that space-time is asymptotically flat. I'm going to assume that asymptotically, omega of k squared is time independent. So omega of k squared is k squared plus a squared m squared plus a term that's a squared r times 6, 1 minus 6c, 1 minus 6c, I guess it's a 1/6 here. So what I'm assuming is that as at a goes to 0, then omega k squared is just k squared. And as a goes to infinity in our universe, where we're starting with de Sitter and ending up with the universe today, that today r is 0, and it's essentially Minkowski space today. As I look out in the universe, this looks like Minkowski space, right? And so in the early universe, omega k squared is k squared. And in the late universe, omega k squared is not going to depend upon r or h. Okay?
Thank you.
All right, so I just have a couple of more things to do. I'd like to finish before today. We want to now define a vacuum. And the vacuum we're going to assume goes by the name of Bunch-Davies. And it will be the in state defining the vacuum state. And defining a vacuum state means that AK in operating on the vacuum vanishes for all values of K. Now, in the Heisenberg picture, which I'm adopting, the states are static. So that's the in state at early time. And then we can define a particle number at some late time in the out state. And this would depend on AK out, dagger, AK out. Now, this is the out ladder operators, but the vacuum state is defined by the in ladder operators. But the in and out ladder operators are defined by a Bogolubov transformation with parameters alpha and beta. So over here, I have AK out defined as AK in, alpha K star AK in minus beta K star AK dagger out. Except, of course, this must be in. So when I construct the particle number at the late time in the out, using the out ladder operators, The thing on the right-hand side is AK out. So this is going to involve beta of K star. And AK star, AK dagger out. Is alpha of K, A, K in. Sorry, this looks like a star, it's K. So this combination of AK out dagger, A out, is just going to give us, when we calculate the vacuum, sandwich it between the vacuum, and I'll write in here, now, this is slightly misleading. We're preparing the system in the in vacuum, and the particles are going to be measured in the out state. Now, I wrote in here, but remember in the Heisenberg picture, the state does not evolve. So I'm preparing the state in the vacuum state. I'm defining a vacuum state at some initial time in, and then the final state will have some number operator that's related to the Bogoliubov transformation, the Bogoliubov coefficient beta that relates the in and out states. Okay, so I am 2 pages of information away from actually calculating particle creation, but you can sort of see the way it goes, that we're going to calculate beta of K squared, and that's going to be an indication of the number of particles in the final state. So I'm preparing the initial state, an initial vacuum. The vacuum doesn't, I'm defining a vacuum in the initial state, and then at the final state, the vacuum will contain some number of particles related to the Bogoliubov coefficient beta of K. So the calculation of particle creation will involve calculating this Bogoliubov coefficient. And I'll be 10 minutes tomorrow morning showing you how that's done. And then we'll get on with it to calculate gravitational particle production.